All right, guys, I'm doing a TRYHACKME Red Team Intro to Windows API. I'm gonna go through task 1 all the way through task 10, and you guys are gonna hear me read this. So, first task, Introduction. The Windows API provides native functionality to interact with key components of the Windows operating system. The API is widely used by many, including red teamers, threat actors, blue teamers, software developers, and solution providers. The API can integrate seamlessly with the Windows system, offering its range of use cases. You may see the Win32 app being used for offensive tools and malware development, EDR, endpoint detection response, engineering, and general software applications. For more information about all of the use cases for the API, check out the Windows API Index. Learning objectives. Understand what the Windows API is, its use cases, and how it interacts with the OS subsystem. Understand how to implement the Windows API in different languages. Understand how the Windows API can be used from various for malicious perspectives, and break down several practical use cases. Before beginning this room, we recommend general familiarity with the operating system architecture. Basic programming language is recommended but not required. This room aims to teach the Windows API at a fundamental level. We will briefly cover implementation of the Win32 API, but we will focus on why and where API calls are used. Please buckle your seatbelt and locate your nearest exit. All right, and then we have to just read that. And it looks like all of this is going to be reading. I don't know if any of this is going to require any type of interaction with an API, but I guess we'll see. All right, task 2, subsystem and hardware interaction. Programs often need to access or modify Windows subsystems or hardware, but are restricted to maintain machine stability. To solve this problem, Microsoft released the Win32 API, a library to interface between user mode applications and kernel. Windows distinguish hardware access by two distinct modes, user and kernel mode. These modes determine the hardware kernel and memory access an application or drivers permitted. API or system call interface between each mode, sending information to the system to be processed in kernel mode. So user mode, no direct hardware access. Access to owned memory location. And then kernel mode, direct hardware access, access to the entire physical memory. For more information about memory management, check out the Windows internal, which was the previous room. Below is a visual representation of how a user application can use API calls to modify kernel components. So your user application down to the API, Win32 API, user mode, user land, switching point, system call, kernel, this is the kernel mode, physical memory, and hardware. When looking at how languages interact with the Win32 API, this process can become further warped. The application will go through the language runtime before going through the API. For more information about runtime, check out the runtime detection and evasion. Does a process in user mode have direct access to hardware? No. Does launching an application as administrator open the process in kernel mode? I don't believe it does. Let me before I answer that, let me scroll up a little bit here and just make sure. No, because user mode doesn't have direct access to it. I'm gonna type no. Okay. Task 3, Components of the Windows API. The Win32 API, more commonly known as the Windows API, has several dependent components that are used to define the structure and organization of the API. Let's break down the Win32 API up via a top-down approach. We'll assume the API is the top layer, and the parameters that make up specific calls are the bottom layers. In the table below, we will describe the top-down structure at a high level and dive into more details later. So layer API, a top-level general term or theory used to describe any call found in the Win32 API structure. So that's the explanation. Layer header file or imports defines libraries to be imported at runtime, defined by header files or library imports, uses pointers to obtain the functional address. Core DLLs, a group of 4 DLLs that define call structures, kernel 32, user 32, and ADV API 32. These DLLs define kernel and user services that are not contained in a single subsystem. Supplemental DLLs. Other DLLs defined as part of the Windows API control separate subsystems of the Windows OS 3.6. Other defined DLLs, NT DLLs, FBE APIs, etc. Call structures defines the API call itself and parameters of the call. API calls. The API call used within a program with functional addresses obtained from pointers, in and out parameters. The parameter value that are defined by the call structures. Let's expand these definitions in the next task. We'll discuss importing libraries, the core header file, and the call structure. In task 4, we'll dive deeper into the call, understanding where and how to digest call parameters and variants. Yeah, we're gonna have to do that. We're gonna have to get our hands dirty because I'm kind of lost. What header file imports and defines the user 32 DLL structure? Well, we know it has a .NET, so there's a hint right there. Let me check. DLL. What header value? What header file? So it's a header file. Define libraries to be imported at runtime, defined by the header file or library import. Uses pointers to obtain the functional address. So header file imports and defines the Win32 DLL structure. All right, let me get a hint. Question requires external research, which I assumed. I was just hoping it wasn't here, because then I'd be so lost. All right, so I'm going to do a Wikipedia search on this. Windows H. Windows H is a Windows-specific header file for the C and C++ programming language, which contains declarations for all the functions in a Windows API, all the common macros used by Windows programmers, and all the data types used by various functions and subsystems. It defines a very large number of Windows-specific functions that can be used in C. The Win32 API can be added to a C programming project by including the windows.h header file and linking the appropriate libraries. To use this function in the XXXX DLL, the program must be linked to the lib.dll. Some headers are not associated with the DLL within a static library. Okay, so makes sense. You know, you would use that if you want to use Windows functions, and if you're creating some types of, you're working on a project using the C language. Okay, so I'm gonna grab that and put it over here. What? That would be the answer. The header file imports and defines. Okay, so apparently that's still not the answer. Oh, I see. It might be one of these down here. So let me see here. Header file imports and defines the Win32 DLL. So I'm just gonna grab this. H. I'm gonna come over here and I'm gonna do a Control F, and I'm gonna look for, see if anything comes up for Windows 32. Win user H. So win user H, user 32 DLL, user service, resource macro. There are a number of child headers that are automatically included in Windows H. Many of these files can't simply be included by themselves. They're now self-contained because of dependencies. Okay, so I guess this is one of those child file headers. And I'll put that in there. Hey, what parent header file contains all the required child and core header files? I think that's Windows H. Because the other one were children, so I don't see how it wouldn't be Windows H. Yep, there you go. All right, task 4, OS libraries. Each API call, the Win32 library, resides in memory and requires a pointer to a memory address. The process of obtaining pointers to these functions is obscured because of the ASLR, address space layout randomization implementation. Each language or package has a unique procedure to overcome ASLR. Throughout this room, we will discuss the two most popular implementations, PInvoke and the Win header file. In this task, we will take a deep dive into the theory of how both of these implementations work, and in future tasks, we will put them into practical use. Okay. Let me see, how much stuff are we gonna need to know here? No, okay, not too much. Window header file. Microsoft has released the Windows header file, also known as the window loader, as a direct solution to the problem associated with ASLR's implementation. Keeping the concept at a high level, at runtime, the loader will determine what calls are being made and create a thumb table to obtain function addresses or pointers. Luckily, we don't have to dive deeper than that to continue working with API calls if we do not desire to do so. Once the Windows H file is included at the top of an unmanaged program, any Win32 function can be called. We'll cover this concept at a more practical level in task 6, PInvoke. Microsoft describes PInvoke or platform invoke as a technology that allows you to access structures, callbacks, and functions in unmanaged libraries from your managed code. PInvoke provides tools to handle the entire process of invoking an unmanaged function from managed code, or in other words, calling the Win32 API. PInvoke will kick off by importing the desired DLL that contain the unmanaged function or Win32 API call. Below is an example of importing a DLL with options. So using system runtime, interop services, public class program. Okay, so you have a class here and it's public, so it's gonna be accessed by other classes. The DLL import, user 32 DLL, character set, Unicode set last error equal true. In the above code, we are importing the DLL 32, right? Yeah, DLL import, and using the attributes of the DLL import. Note, a semicolon is not included because the PInvoke function is not yet complete. In the second step, we must define a manage method as an external one. The external keyword will inform the runtime of the specific DLL that was previously imported. Below is an example of creating the external method. Okay, using system runtime, interop services, public class program, private, static, intern, extern, int, message box, int ptr, string, IP text, string, IP caption, uint, utype. Okay, so intern is a keyword will inform the runtime of specific DLL that was previously imported. Okay. Now we can invoke the function as a managed method, but we are calling the unmanaged function. We will cover this concept at a more practical level in task 7. What overarching namespace provides PInvoke to .NET? Which overarching namespace provides PInvoke to Dart.NET? Oh, that's a good question. Well, I'll do this. I will take this .NET and I'll do Control F. Oh no, it's not giving me the answer. Okay. I'll go with external. Dang it. Overarching namespace provides .NET. System. Hey, using system. So I've done some C# coding in the past, and I know that using system and just specifying, I don't know if you would call these like modules. I haven't done C# coding in a while, but specifying what you're using up here is important. Otherwise, the code down here won't be recognized. So I do know using system is pretty important when you're writing your code. What memory protection solution obscures the process of importing API calls? So the ASLR, that what it does is it assigns. I know it somehow like it assigns the memory for an application randomly, so that the application is not vulnerable to like buffer overflows. So I'll just say that. Yeah. All right, cool. Task 5, API call structure. API calls are the second main component of the Win32 library. These calls offer extensible and flexibility that can be used to meet a plethora of use cases. Most Win32 API calls are well documented. Understand the Windows API documentation and PInvoke.net. And in this task, we will use an introductory look at naming schemas and in and out parameters of API calls. API call functionality can be extended by modifying the naming scheme and appending a representational character. Below is a table of the characters Microsoft supports for its naming schema. Okay, characters. A represents an 8-bit character set with the ANSI encoding. W represents a Unicode encoding. EX provides extended functionality or in and out parameters to an API call. Go ahead and minimize that. For more information about this concept, check out the Microsoft documentation. Each API call also has a predefined structure to define its in and out parameters. You can find most of these structures on the corresponding API call document page of Windows documentation, along with the explanation of each I/O parameter. Let's take a look at the write process memory API call as an example. Below is the I/O structure for the call obtained. So bool write process memory in handle process in LP void LP base address and in LP void LP buffer in size /t in size out size /t wildcard LP number of bytes written. For each I/O parameter, Microsoft also explains its use, expected input and output, and accepted values. Even with an explanation, determining these values can sometimes be challenging for particular calls. We suggest always researching and finding examples of API calls usage before using a call in your code. Okay. Which character appends to an API call represents an ANSI encoding. So they mentioned that up here, so that would be A, so capital A. Which character appended to an API represents extended functionality? Extended functionality, so that would be EX, right, EX. What is the memory allocation type of that in the virtual allocate API called? Oh, that's a good question. Something tells me I'm going to have to research this one. All right. Let me click hint here. Remember, all I/O parameters can be found in the Windows documentation. Okay. So what is that? Memory allocation type of, okay, so we'll just look this up. What is the memory allocation type of this in the Windows documentation? That's a Windows documentation, right? Not the Microsoft documentation. Yeah, okay. Click here. And I'm gonna do Control F. Oh no, thought something would come up for that. Okay, I'm not seeing it here. So let me go back over here. I usually have to open up 2 windows when I'm switching between pages here. In the Windows, okay, let me see if I can look it up with this instead. Oh, no, nothing came up for that. Come on, come on. Oh, wait, this is the wrong one. All right. Windows documentation. And let me grab that. Close that out. Over here. Oh, no luck. Try deleting that. Virtual hard disk. What do we got next here? Windows Virtual PC, Virtual Server. Windows Central. Nope, I'm not seeing it. All right, let me memory allocation of in the virtual allocate API call. All right, let me try looking this up again. Oh, that doesn't bring up anything. Are they sure it's in here? Remember, the I/O parameters can be found in Windows documentation. I/O parameters. Okay. Maybe it's I/O slash. Oh, here we go. File and I/O local files. Okay, this is probably right here. Oh no, it's gonna be a rabbit hole. It's gonna be a rabbit hole. 32 file controls. I guess we'll just click on this one, see what it takes. I don't think this is it. Let me go back. This control codes. This might be it. I could see this being it. Yeah. But I'm not trying to look through all these. So what I'm gonna do is I'm gonna pause it. All right, I found it. The way I found it is I just took keywords here. So this is virtual allocation, I'm guessing, but it's kind of like an acronym almost. And then I came over here and there's this little search bar on the left and I just threw it in there. When I threw it in there, it took me to this page here. It kind of looked like this. And I was like, oh, let me just click on this first one. That took me here. And then as I was going down, we see some values and the meaning of those values for the virtual allocate function, which reserves, commits, or change the states of a region of a page in virtual address space of the calling process. Memory allocation by this function is automatically initialized to 0. And if I scroll down, there is a one with an 8 here, and that's the one I was looking for. Indicates that data in the memory range specified by the IP address and DW size is no longer of current interest. The page should not be read from or written to the page file. However, the memory block will be used again later, so it should be decommitted. This value can't be used with any other value. Right, okay. And I just threw it in there and it worked. So that's it right there. Task 6. Oh, this is getting a little harder. Microsoft provides low-level programming language such as C and C++ with a predefined configured set of libraries that we can use to access needed API calls. The Windows H header file, as discussed in task 4, is used to define call structures and obtain function pointers to include window headers pre-appended aligned below to any C or C++ program, include windows.h. Let's jump right into creating our first API call. As our first objective, we aim to create a pop-up window with the title Hello THM. Using the create Windows EXA to reliterate what is being covered in task 4, let's observe the in/out parameter of the call. So we have Windows A, which if I remember, when you append something to it, the A means represent an 8-character set with ANSI encoding. Okay, so that's what that A is signifying. And D word, DWEX style, optional Windows styles, and then we have some other stuff like Windows class, Windows text, Windows style, X position and Y position, width size, width height, parent windows, menu, instant handles, additional application. Okay. Let's take these predefined parameters and assign values to them. As mentioned in task 5, each parameter for an API call has an explanation of its purpose and potential value. Below is an example of a complete call to create Windows EXA. So this one's interesting. With that out of the way. HNW create Windows EXE. It's almost like, I mean, this API, it's got like a value and key pair, right? And then we have these values here, which will help us create this pop-up window. So class, hello, THM, WS, overlap windows, CW user default, and CW use default. Okay, null instance. We define our first API call. Now we can implement into an application and use the functionality of the API call below in this example application that uses the API to create a small blank window. Okay, so we've said we define our API call. So we have to define it first. So this is us defining it then, right? And then, okay, then we define the first API call in C. Now we can implement it in an application by using the functionality of the API call below as an example of application that uses the API to create a small blank window. Okay, bool create, and then window name, dword, x values default, y values default, width, height, h menu, derived from Windows proc, get module, null, class name, register class, Windows, All right, cool. So, all right. So, I mean, in coding, I kind of figure this is kind of like initializing it, and then this is kind of um, like, or more like, yeah, like declaring it or initializing and actually using those values. If successful, we should see a window with the title box, hello, THM. As demonstrated throughout this task, low-level language make it very easy to define an API call quickly because of the ease of use, extensibility. C-based language are most popular among the threat actors and vendors alike. Do you have to define a structure to use an API call? I'm going to say yes. Yes, you do. Oh, okay. I'm going to say no because that's the answer. All right. All right, cool. Oh, I guess that's pretty cool. Too bad they don't give us like a little environment to run this in, I guess. Yeah, it is what it is. Task 7. As discussed in task 4, the PInvoke allows us to import DLLs and assign pointers to the API call. To understand how PInvoke is implemented, let's jump right into an example below and discuss individual components afterwards. Win32, DLL, kernel 132, public, static external int per, get computer name, string buffer, LP buffer. The class function stores defined API calls and a definition to reference in a full future method. The library in which the API call structure is stored must now be imported using the DLL import. The imported DLL acts similar to the header package, but required that you import a specific DLL with the API call you are looking for. You can reference the API index or PInvoke.net to determine where a particular API call is located in DLL. From the DLL import, we can create a new pointer to the API we want to use, notably defined by int etr. Unlike the other low-level languages, you must specify the in-out parameter structure in the pointer. As discussed in task 5, we will find the in-out parameter for the required API call for Windows documentation. Now we can implement the defined API call into an application and use its functionality. Below is an example application that uses the API to get the computer name and other information of the device it runs on. Win32, import DLL, kernel32, public stack, extern int get computer name string, all right, static void main string argument, bool successful string buffer size get computer name reference size console write line to string. If successful, the program should return the computer name of the current device. Now that we've uncovered how it can be accomplished in .NET, let's look at how we can adapt the same syntax to work in PowerShell. Defining the API call is almost identical to .NET implementation, but we need to create a method instead of a class and add a few additional operators. So method instead of class, okay, DLL import 32, public stat, public name, kernel, public status, get module string, LP, module name, DLL import 32, public stat, external boolean, virtual protection, in PTR IP address. Okay, gotcha. The calls are now defined by PowerShell, required one further step before they can be initialized. We must create a new type of pointer for each win DLL within the method defined. The function add type will drop a temporary file in the temp directory and compile needed functions using CSCEXE. Below is an example of the function being used. Kernel add type method definition name kernel 32 namespace pass through. Okay, we can now use the required API call with the syntax below. What method is used to import a required DLL? Import a required DLL. Add type. Import call. DLL import. I feel like it would be that DLL import. Got it. What type of method is used to reference the API call to obtain a struct? All right, I need a hint. Mention in task 4. Oh, okay. So let me go back to task 4. Oh, this one. I think it's extern. If not, I'm gonna just control F it and I get back over here. That's my guess. Yeah, I don't think that was right. So let me, I remember reading that word, so I definitely remember it being here. Yeah, so PInvoke, the callback function. And guys, if this is kind of going over your head, I'm totally with you right now. But one thing I've learned in technology is just bear with it. If you don't understand something, it's fine. As you go through the ropes, it'll start to make more sense. It won't make much sense at first, though. What method is used to reference the API to obtain a structure? Oh, I guess that's not the answer then. Type of method. Oh, method. Oh, method. Okay. So method. Create a class. Method. Few operators. PowerShell. Few features to initialize. Pointer for the Win32 DLL within the defined function. Add type will drop a temporary file. What type of method is used to reference the API call to obtain a struct? Type of method. They mentioned task 4. So, okay, let me look for method. Here we go. Oh, I know it's not that. A semicolon is not included in the P function, but is not yet complete. In the second step, we define a managed method. Managed. I don't know. Managed. It has to be managed. We invoke. Okay, let me pause it on my side because this is going to take me a minute. All right, I honestly didn't know the answer. I had to turn to Google. I did it, and it brought me to the TRYHACKME page, and I looked down here and I found it. So someone gave a hint. He's just like, for those still stuck, I'll stress out that you'll find the answer in task 4. Focus on searching not the method, but its type, plus the answer is hidden in the previous 2 messages. And I read this, and you have any hint for an external source? I'm still learning for the coding stuff. Yeah, external. So I seen external. I was like, yeah, I remember extern, and I tried using that. That didn't work. Remember, that was like the first one I tried. It didn't work. Well, I just had to spell the whole thing out, I guess. Now let me look back at test 4. Maybe it's in here somewhere. I'm not seeing it. I mean, that's the first one I tried and it didn't work. All right, task 8, commonly abused API calls. Several API calls within the Win32 library lend themselves to be easily leveraged for malicious activity. Several entities have attempted to document and organize all available API calls with malicious vectors, including sans and malapi.io. While many calls are abused, some are seen in the wild more than others. Below is a table of the most commonly abused API organized by frequency and the collection of samples. API calls and explanations. Load library A maps a specific DLL into the address space of the calling process. Get username A retrieves the name of a user associated with the current thread. Get computer name A retrieves a BIOS, a net BIOS or DNS name of a local computer. Get version EXA obtains information about the version of the operating system currently running. Get module file name A retrieves the fully qualified name for the file of specified module and process. Get startup info A retrieves content of the startup info, structure, Windows station, desktop, standard handling, and appearance of the process. Get module handling returns a module handle of the specified module if mapped into the calling process address space. Get process address returns the address of a specified export DLL function. Vital protection protect changes the protection of a region of memory in the virtual address space of the calling process. In the next test, we'll take a deep dive into how these calls are abused in a case study of 2 malware samples. Oh, fun. Which API call returns the address of an exported DLL function? Get process address. Yes, I do control F a lot. Let's see. Which API call imports a specific DLL into the address space of a calling process? I think it's this one. Oh wait, we just used that one. Okay, I think it's this one then. Dang it. All right. Well, let me do this here. Specified. All right, that doesn't help. Address. Okay, get module handle. Has to be this one. Oh, come on. Which API call imports a specified DLL into the address space process? It has to be this one then. Oh, wait. Load library 8. Maps a specified, maps a specified DLL into the address space of the calling process. Yes, that's it. If only I would read. Yes. Task 9, malware case study. Now that we understand the underlying implementation of the Win32 library and commonly abused API calls, let's break down 2 malware samples and observe how their calls interact. In this task, we'll be breaking down a C# keylogger and shell code launcher keylogger. To begin analyzing the keylogger, we need to collect which API calls and hooks it is implementing. Because the keylogger is written in C#, it must use p/invoke to obtain pointers of each call. Below is a snippet of the p/invoke definitions of the malware sample source code. All right, import URL. Key, okay. All right, very cool. Below is an explanation of each API call and its respective use. API calls. Set Windows hook exe. All right, so we see this ex installs a memory hook into a hook chain to monitor for certain events. Unhook winhook.exe. Ex actually. All right, here it is here. Remove and install hook from a hook chain. Get module handle returns a module handle for specified module if mapped into the calling process address space. Here, get current process retrieves a pseudo handle for the current process. To maintain the ethical integrity of this use case, we'll now cover how the sample collects each keystroke. We'll analyze how the sample set a hook on the current process. Below is a snippet of the hooking selection of malware sample code. Hook. Okay. Let's understand the objective and procedure of keyloggers and assign their respective API calls for the above snippet. Using the API document and the contents of the snippet below, begin analyzing keylogger using question 1 through 4 as a guide to work through the sample. Oh no. Oh gosh, this one has so many. Wow. All right. All right, cool. Well. Okay, time to get started then. They really saved the best for last, didn't they? So let me look through this. What Win32 API is used to obtain the pseudo handle of our current process and the keylogger sample? That's a good question. Get current process, I'm guessing, or int per. Yeah, I think it's that one. Get current process. Hey, I got it. I mean, I just kind of guessed on that one, to be honest with you. I just assume that, you know, if you have this and this is kind of like your, I don't know what you should call this, is like a function. Okay, what Win32 API is used to set a hook on our current process in the keylogger sample? So they just mentioned which one was that. It's the set Windows hook. Or it might be set hook. It's one of those two. I'm guessing it's this one though. Just because of the length of the little asterisks there. Yeah. What Win32 API call is used to obtain a handle for the pseudo handle in the keylogger sample? Obtain a handle. Scroll back up here. Get module handle. I mean, they kind of explain this. I don't think you need to actually take a look at that document, to be honest with you. What Win32 API call is used unset the hook. Okay, they already explained that. It was the unset, unhook Windows, this one right here. So these are API calls. Okay, gotcha. What Win32 API is used to allocate memory for the size of the shellcode? Okay, so now we're getting to shellcode. To begin to analyze the shellcode launcher, we once again need to collect which API call it is implementing. The process should look identical to the previous case study. Below is a snippet of the PInvoke definitions of the malware sample code. All right, virtual allocate, wait for a single object, create thread. Below is an explanation of each API call and its respective use. API call explanation. Virtual allocate reserves, commits, or changes the state of region, a page, and virtual address space of the calling process. Wait for a single object. Wait until a specified object is in the signal state or the timeout interval elapses. Create thread creates the thread to execute within the virtual address space of the calling process. We'll analyze how the shellcode is written and executed from memory. Okay, very interesting. Let's understand the objective and procedure of the shellcode execution, then assign the respective API calls for the above snippet. Using the Windows API documentation and the contents of the above snippet, let's begin to analyze the shellcode launcher, answering questions 5 through 8 as a guide to work through the sample. Okay, what Win32 API is used to allocate memory for size? Okay, so allocate memory. So I would say it's gonna be this one right here. Virtual allocate. What native method is used to write shellcode to an allocated sector of memory in the shellcode launch sample? We got a dot in there. Let's see. Shellcode length. What is the question asking again? What native? Marshall copy. I think it's Marshall copy. It's got the shell code length in there as well. Okay. What Win32 API call is used to create a new execution thread in the shellcode launcher sample? A new. Probably this one, wait for a single thread, or create thread, I think was that one. So this one, this bottom one, obviously, because the asterisk, I'm just gonna say that's it right there. Used to wait, yeah, so wait for object. I mean, it's pretty self-explanatory in the sense that whatever they're asking is basically in the API call. So, oh, there we go. All right, conclusion. This is the end of the basics of Windows API, the functionality and extensibility of the API have many other possibilities and applications that we did not mention in this room. The Windows API can serve you for various use cases, as we will continue to discuss and explore throughout the Red Team path and other rooms on TRYHACKME. Okay, all right, click here. Yeah, I love this. Yay, confetti. All right, so guys, that's it. This took me a good minute. Totally went over my head a little bit. It's okay though. This was the intro. I kind of learned something new. I learned that, apparently you can use these Win32 APIs to, call and basically establish shells and make keyloggers. Very interesting. I can see how that would go under the radar if you're a blue teamer. That probably wouldn't be picked up by a firewall. So very cool. Too bad we didn't get to execute any of these in like a little lab environment. I would have loved to do that, but I'm pretty sure we're going to have that opportunity later down the road. And this is just an intro. So very basic, just understanding what the Windows APIs are. They have key value pairs that you basically will initiate, and then you'll get a return value in the form of possible, keyloggers or shell launchers, if you really understand what you're doing. I'm not a C# programmer. I mean, I'm not a C++ or C+ or C programmer. I did some C#, and I actually have some videos of that in the past. But I probably don't know too much about this to really talk any more than this intro. So let me go to my dashboard, see where we're at, see what the next one's going to be about, and whether or not I'm going to make a video for it. Because if we look at this, I didn't make a video for Windows internals. Didn't figure I need to be honest with you. There's plenty of videos out there, and I tend to focus on the ones that will gain either the most views or I notice people need help with. There's just not enough videos out there, because if I'm struggling, you're struggling. If there's no videos out there, I'll definitely make one. So abusing Windows internals. So I guess this is another Windows internals lab here, which is cool, I guess. Oh yes, Windows internals. This one looks pretty cool. All right, looks like a lot of stuff I'm not going to understand and very complicated diagrams. All right, cool. I like being on the struggle bus, so this is right down my alley. DLLs. Cool. Yeah. All right. All right. Maybe I'll make one. Maybe I'll make one tomorrow. But I really can't wait to complete this. Let's see, intro to antivirus. That one sounds kind of cool. Oh, go ahead. Deploy VM. Finally, we get to deploy VM. All right, I look forward to that one for sure. Um, but hey, you know what? Learning about this complicated stuff, this is stuff we have to learn, right? This is stuff that's going to set you apart from people who are, um, just being script kiddies. Just getting the guts, understanding the ones and zeros. That's what it's all about right there. So anyhow, look forward to making that video. Y'all have a good one. Danny out.